Okay, we're going to finish up our discussion on surface area and volume of solids by looking at similar solids, and we're going to kind of go back a little bit. We've talked about this before when we looked at area and perimeter, and one of the things that you may remember is that for a given scale factor, and SF I'm going to use to represent scale factor, of A to B, the ratio of the perimeters was also A to B because it stayed in one dimension, whereas the ratio of the areas was A squared to B squared because we went to two dimensions. We're going to use this idea as we talk about surface area and volume of similar figures. Now, a little bit of a review. Remember, similar solids, just like similar shapes, have the same shape and all the corresponding dimensions are proportional. So we determine similarity the same way. We look at the corresponding sides and see if they all have the same ratio. So if I look at these sides, 3 corresponds to 6, so I have 3 to 6, which reduces to 1/2. So I have to check to make sure all of them are also going to reduce to 1/2. So if we look here, 3 to 6, that's the same thing. It will reduce to 1/2. So far, so good. Now we have 2 and 4. So 2 to 4, that reduces to 1/2. Since all of these are the same, they are similar, and the scale factor is that proportion. And since we're going from the first figure to the second figure, we go 1 to 2. Now remember, we might also see it written in this way, but it's the same thing. Now if we look at these two figures to go from the first to the second, if we look first at the height, so we have 2 to 3, that does not reduce. Then if we look at, I'm going to call it the length of the figure, so we have 3, and over here we have 6. That reduces to 1/2. Those two numbers are not the same, so these two figures are not similar. And we don't even have to check the third pair to see, because we've got these two that aren't the same. Now for the cylinders, we're going to compare the radius. So first to the second, we have radius of 6 to 5. That does not reduce. Then we look at the height. We have 12 to 10, which does reduce to 6 to 5. So these two are similar, and the scale factor of SF, the scale factor, is 6 to 5. Or remember, we might see it written in this manner, 6 to 5. Now, as we looked at the ratio or the scale factor and how it goes to the ratio of perimeters and volumes, or perimeters and areas, we're going to use the same thing with areas and volumes. Areas is the same, A squared to B squared. Volumes, again, because we're working now in 3 dimensions, we have A cubed to B cubed. So for any scale factor, A to B, for areas, you square each of those. For volumes, you cube them. So if we look down here at the bottom, we have square prisms that are similar. We want to know the scale factor of the smaller prism to the larger prism. So remember, A cubed to B cubed. So we're looking at volume. So smaller is 729 to the larger is 1331. All right, the first thing I want to do is take the cube root of each of those, and hopefully it'll be a perfect cube. Well, if I look at 729, I find that that is 9 cubed. 1331 is 11 cubed. So the scale factor of the smaller to the larger is 9 to 11, A to B. Remember, we could also have it written this way, 9 to 11. Well, let's see if we can use that in this example. We want to find the scale factor of two similar prisms with surface areas of 144 and 324. Remember, area is A squared, B squared, and we're looking for A to B. That's what we want. Well, A squared to B squared is 144 over 324. Now, I know that 144 is a perfect square, so I could reduce this first, but since I know that 144 is a perfect square, let's go ahead and check and see if 324 is also a perfect square. If it's not, then we'll reduce and work from there, but if it is, might as well go ahead and take the square root of it. So 144 is 12 squared. When we check 324, we find that yes, it is a perfect square. It is 18 squared. So A is 12, B is 18, but 12 over 18 will reduce because both are divisible by 6. So we have 2 to 3. So the scale factor of these two similar prisms is 2 to 3, or we might see it written this way, 2 to 3. And we can also use scale factors to help us find other dimensions. In this example, the lateral areas of two similar paint cans are 1,019 square centimeters to 425 square centimeters. And that's area, so it's A squared to B squared. Important to keep that in mind. We want to know the volume of the larger can if the volume of the smaller can is 1157. So remember, volume is A cubed and B cubed. So we need to find out what A and B are. Well, neither of these two numbers are perfect squares, so A over B would simply be the square root of 1,019 over the square root of 425. So if we then cube those, we have 1,019 quantity cubed over square root of 425 quantity cubed, and that equals the volume of the larger can to the volume of the smaller can, which is 1157. Now to solve this, since the volume of the larger can is being divided by 1157, we're going to multiply both sides by 1157. So 1157 times the square root of 1,119 cubed, and all of that is divided by the square root of 425 cubed. That is the volume of the larger can. We then go and use our trusty calculator and put that into our calculator, and we find that the volume of the larger can is approximately, I'm going to round it to 2 decimal places, 4,295.48. Our unit is cubic centimeters. Okay. Now for another example, here we have the volumes of two similar solids are 128 cubic meters and 250 cubic meters. The surface area of the larger solid is 250 square meters. What is the surface area of the smaller solid? Well, we start with volume, so A cubed to B cubed, that's 128 to 250. Now, I'm going to start by reducing these. I reduce them both by 2. I get 64 over 125, both of which are perfect cubes. 64 is 4 cubed, 125 is 5 cubed. So the scale factor A to B is 4 to 5. Now we can use that to find surface area. Remember, surface area is A squared over B squared. So we're going to have 4 squared over 5 squared. And we're given the surface area of the larger solid, so that's this one down here, is 250. What is the surface area of the smaller solid? So surface area of the smaller one. It's being divided by 250, so we're going to multiply both sides by 250. So 250 times 4 squared divided by 5 squared equals the surface area of our smaller solid. We do that multiplication, we get 160. Our unit is square meters. So that is the surface area of our smaller solid. For our last example, now we're going to use scale factor to find capacity. So in this example, a bottle that is 10 inches high holds 34 ounces of milk. The sandwich shop shown is shaped like a milk bottle. To the nearest 1,000 ounces, how much milk could this building hold? Now, we know a bottle that's 10 inches high, and this one is 480 inches high, so we have a scale factor of 10 to 480, which reduces to 1 to 48. So that's our scale factor. Now, if we're looking at quantity or how much capacity it holds, what we're looking at is actually volume. So we need A cubed and B cubed. Okay, well, A cubed is going to be 1 cubed. B cubed is going to be 48 cubed. And if we look at, we know that the 10-inch bottle holds 34 ounces. And we want to know how much the building holds. That's our unknown. Okay. First, I'm going to simplify this, so I get 1 And then 48 cubed, if we put that into our calculator, we get 110,592. And that's 34 over x. Cross multiply, 1 times x is x. That comes out nice and convenient. 110,592 times 34 is this number. And we want to know to the nearest 1,000 ounces. Here is our thousands place. All right, so we're going to look at this number to determine how to round it. So everything in front stays the same. Now, since 1 is below 5, this stays the same. So 3,760,000 ounces, approximately. All right, so that's how we can use scale factor. Again, remember, for a scale factor of A to B, area is A squared over B squared. Volume is A cubed over B cubed. Perimeter, going back to the previous chapter, is A over B. Okay.